I'd like to go over some of the various ways to set up shell mesh definitions in SOLIDWORKS Simulation and when you want to use them. There are timestamps in the video description below if you'd like to jump ahead to any particular section. So I'm just going to create a new part file, and we'll just represent a simple cantilevered beam. So I'm just going to sketch a rectangle here, set it off the origin, and I'll make this maybe 20 millimeters wide by 80 millimeters long. And I'll extrude that to a depth of 2 millimeters. That'll be my beam. And I'll load up the SOLIDWORKS Simulation add-in so we can set up a study here. And this is going to be using a solid mesh at first. So we'll just use all the default settings. And then we'll compare how and why you might want to switch to a shell mesh definition. So once I have my simulation add-in loaded, I'll create a new study. Choose static as my type, and let's call this solid. Now to set up our simulation, I'll apply a material. So I'm just going to apply a plain carbon steel. I'll set a fixture. So I'm just going to apply a fixed geometry fixture to the back face of the model here. And we'll apply a load to the front face of the model. And we're going to want to orient that so it's pointing down. So I'll choose selected direction and just choose one of the vertical edges of the model. And let's try a force of 20 newtons. Now if I just click run, it's going to mesh and run using the default settings. This is going to produce what's called a solid tetrahedral mesh. And we can visualize that mesh either overlaying it on the results by right-clicking on the legend and showing it. We can see there that they're represented by solid elements that go through the thickness of the material. We can also do something like a mesh sectioning if we want to be seeing those elements through the thickness. So whenever we happen to have particularly thin geometries or wide and long thin geometries like this, the solid mesh ends up being a little bit inefficient. We can oftentimes save computation time by modeling this as a shell. One of the big requirements here though is that we have a constant wall thickness. So let's take a look at how we'd set up a study with a shell definition. I'm just going to create a new study here, and we'll call this shell defined by faces. Now this is my preferred way for setting up shells. So we can see the icon on the top of the tree that indicates this is a solid, that little cube icon right there. If I right click on that, I can choose to define shell by selected faces. And basically in this simple example, I'm just going to need to select one face. So I'll just select the top face of the model here, but you could pick the top or the bottom. And you can see with the preview enabled, we can essentially see what's happening here. A shell is a definition essentially that has no thickness in terms of the mesh, but the thickness is kind of an applied property that we can adjust here. So I happen to know this was 2 millimeters thick, so if I set that to 2 millimeters, that preview is going to show up representing the thickness of the beam. However, you can tell it's not offset correctly. So we have down here this offset section, and we can choose where that thickness is essentially applied, and I'd want to choose the bottom surface such that they line up. You can see here different options on how you might flip them. Just want to make sure that's lined up with our actual solid model, because essentially we'll be replacing the solid model we see on the screen with a special shell mesh definition. We can also choose thin versus thick for the shell definition type. I generally default to thick now if there's any question. If it's not an extremely thin file, then the thick formulation is going to be more accurate in predicting bending stresses. with minimal performance downside. So I'll click the check mark there to accept that. And if we just go and generate the mesh manually, I just want to show you what we're looking at here in terms of the mesh that gets generated. So we just see a kind of planar representation of the shell. So there's no thickness there really, but there is a thickness parameter that's applied. And if we right click on the mesh, we can render that thickness in 3D, so we can kind of get back to what looks to be like the entire solid model. So we can perform this very quick conversion essentially on the fly, and this works in your assemblies also. You just want to make sure you select all the faces that would make up either the inside or the outside of that body that you're working with. You can always go back and edit the definition again if you need to see which face you selected, or edit the thickness or offset values. Okay, so from here we can proceed like the previous setup. Apply the material that we want to be working with. And when we go to apply fixtures, this is where it gets a little bit interesting, because let's think about what is actually defined in the simulation. As far as the simulation is concerned right here, as you saw when we generated the mesh, it's only really this top face that exists. So if I tried to use the same exact fixture scheme that we had previously, like selecting the back face and click the check mark, we're going to get an error message that tells us to select an entity on the shell. You might be wondering why this is happening. Again, as far as the simulation is concerned, only that top surface essentially exists there. That's where our mesh is. So we need to select something from that top surface, which in this case, I can select that edge, that back edge. And it just so happens that if we fix the edge of this shell, the end edge, that'll be similar to as if we fix the entire back face on a solid. So it's going to be the same thing when it comes to the load. So I'll choose this upper edge of the shell, choose the selected direction, and we'll turn on the force and set that to the same 20 newtons, pointing downward. And we should be ready to run this now. And we expect to see very similar results to our solid mesh. So we can use the compare results function if we want to, and compare all studies. Compare maybe the stresses and displacements between these two studies. And despite the difference in kind of the visualization, we can see our numerical values for stress and displacement are remarkably similar. However, we're using many less mesh elements on the right, and if we got in terms of trying to refine the mesh to improve our results, we'd see that disparity just grow and grow, where the solid model is going to consume more and more elements to try to refine it, whereas the shell will not scale up as badly because it's not filling out a solid volume there. So just a little bit of extra setup work and we can save ourselves some solve time. Now, one thing to be aware with the shell mesh in terms of post-processing, if we go to edit the shell mesh results, we'll see under our definition that there is both a top and bottom component to the stress. So the shells had that orange and gray face, which represent the bottom and top. And if we flip the stress component here, you can sometimes see a difference in the stress results. This particular model appears to not really have a difference, but a substantial viewable difference. But you will want to check for your shells both the top and bottom stress, or through your options enable the render shell thickness in 3D, which will kind of do that 3D overlay of the top and bottom. Just realize that any of the stress that you see on the side here is not very not accurate at all, really. Anything you see just through the sides, we're not getting any prediction through the thickness of the material. We're really just looking at the top and bottom stresses overlaid on a render here. So generally I prefer to just view them in the 2D mode and flip through if I need to. So this was a very manual shell definition, but there's two other workflows that are quite straightforward in SOLIDWORKS. So if you happen to be using a sheet metal part, using the SOLIDWORKS sheet metal features, when you go to create a new study in here, it's going to automatically convert that to a shell. So we see yet a different icon here representing a shell mesh definition. We can see if we create the mesh on this model, it's going to be represented by a shell, auto-converted. And if we try to edit the definition of this particular shell, we'll see that those values are grayed out because those are essentially carried over from the sheet metal properties. So if you wanted to edit that thickness, you would go back and edit the sheet metal model. But then there's other benefits to the sheet metal conversion, such as it doesn't care which selections we make. I can choose cylindrical faces, I can choose particular edges, and it won't give me those errors about selecting an entity on the shell. So we can very quickly set up a sheet metal model using these types of definitions and still take advantage of our shell. Sometimes you may have an imported part. So let's look at the case of an imported version of the same file. Then it won't recognize automatically that there's a shell mesh definition. So there's a couple approaches. We could still use the define shell by selected faces. If I click on this, this is looks like it's 0.1 inch thick. So if I create a study, I could right click define shell by selected faces on here. And a shortcut is I can right click a face and choose select tangency and then just input that thickness. Make sure that's applied to the correct side once again. And there's my shell mesh definition. Again, if I go this route, I need to be careful to remember which side I'm selecting. In this case, it's the outside set of faces. And if I ever need a refresher on that, I can just click on the shell mesh definition and you'll see that highlight there. It's also very important, as I mentioned, to make sure you select them all. If I were to exclude one by accident, and then I recreate the mesh, you're going to see essentially that whole chunk of the geometry missing. So when you use these manual definition tools like define shell by selected faces, it's really on you to make sure that they're set up correctly. Let's look at an alternate way. I'm just going to delete that study. And again, if you think it's a sheet metal part, but it's an imported body and it doesn't have the sheet metal features, a trick I've used is to activate your SOLIDWORKS sheet metal tools and then use the insert bends command. So you can choose insert bends, and this allows you to pick a fixed face of the part and essentially turn this into a native SOLIDWORKS sheet metal feature. So you'll see here it will actually try to flatten and then process the bends. And as long as this works, where it's able to generate the flat pattern, then we've essentially converted an imported body into a native sheet metal part. And then if I go to create my simulation study, I should automatically have my nice shell mesh definition once again. It is worth noting on very large complex sheet metal parts or complex assemblies, this automatic conversion can take some extra time, and then you may want to consider, if that time is really bogging you down, you could consider using the define shell by selected faces or using this next method we're going to look at, which would be using a surface model. So let me create one more part and we'll take a look at using a surface model based approach. Now, I would typically only recommend this if you were building a dedicated model just for analysis, but if we do create SOLIDWORKS surfaces, these will automatically come into the simulation as shells. So let's suppose I want to create something like create a back plate here. So I'll use a center rectangle. And I just want that to be a flat surface, so I'm going to choose the planar surface command to convert that into kind of a base plate there. And then maybe I want some kind of profile coming out of that. Let's say it's like a square profile. That would be like a square tubing. So then I could create this secondary profile here. And I'll use this for an extruded surface. So these are now two separate surface bodies in my SOLIDWORKS feature tree. And when I go to create a simulation, they'll show up in my simulation as two separate shells. Now these have a kind of an extra requirement where you can see their thickness not defined. So these require us to go in and edit the shell definition and assign the appropriate thickness. So if I say these are going to be 1/8 inches thick, then it's going to offset the shell to whatever side that I specify. And I'd have to specify that also for the other side here. Maybe this one's 1/4 inch thick. Component contact should be applied, so when we have things like global bonding, that should affect these. So I should be able to fixture one shell and let's say apply a force to the other side. So again, just do a straight downward force here for us. And of course I need my material. Now let's take a look at the mesh and then we'll see if this will run for me. So we can see the mesh that's generated here, all shell mesh. And if we want, we can look at the contact visualization plot by clicking on the connections folder and activating that, and that'll show me that if the bonding is occurring and where it's occurring. If I don't see it everywhere that I wanted it, like it seems like in this case, then I might want to manually specify contact. So we could always go in and set contact sets between different faces. So I can choose different edges or faces. I might just select all 4 of these edges here from the kind of square channel that I created, and then the one face of this other shell. Then we don't have to rely on our global contact. We should have now a nice local contact set definition there. So when you are manually converting things, flipping things back from shell to solid, you do want to take care to validate your contact conditions when you get into assembly level analysis. And then there we can see the preliminary picture of what our stresses and deformations will look like with this model setup. So we discussed 3 workflows for setting up these studies using shell mesh definition. We have the ability to define shell by selected faces, which allows us to kind of on the fly convert a solid component from a simulation study into a shell mesh definition. That requires paying some extra attention to make sure that all your settings, your boundary conditions and mesh controls and contacts are applied to the set of faces that you defined the shell from. We looked at how sheet metal parts automatically convert into shells in simulation. They don't really require any extra input. Then we looked at how surface bodies can also be used to create kind of a purpose-built model for a shell mesh simulation. If you think this seems like a lot of work or a study setup in terms of picks and clicks, then you might want to check out a couple tools which speed up these processes for larger assemblies. So the first would be the Shell Manager, which allows batch selection of shell definition, color coding shells by their thickness values, and grouping them into sets so that you can quickly vary the thickness parameters. So you can access the Shell Manager and visualize which shell definitions still need to be applied, which are grouped together, and so on. It's a very valuable tool. And the other thing I would recommend is the Import from Studies feature, which allows you, in the case of an assembly level analysis, to set up things like your shell definitions on child components and then import those back into the top level study. So if those interest you, then check out the additional videos linked in the video description below for more details. And let us know if you have any other questions on using SOLIDWORKS Simulation.